All right, welcome to part 2 of 11.3. So we're going to start looking at vectors that are perpendicular. So we say two vectors are orthogonal if and only if they are perpendicular. Lines or planes are perpendicular. A vector that is perpendicular to a line or a plane is called a normal vector. So again, if two vectors are perpendicular, they're called orthogonal. Lines or planes are perpendicular. We can have that. But when they're vectors, we call them orthogonal. Now, if we mix the vectors with the line or the plane, so if a vector is now perpendicular to the line or plane, it's called a normal vector. So I know there's a lot of crazy definitions going on in here, so just be prepared to use them properly. Two non-zero vectors, A and B, are parallel if there exists a non-zero scalar, we'll call it C, such that A is equal to CB, and to solve for that scalar value C, we'll just divide vector A by vector B. In other words, you just divide the x, the y, and the z components. So in example 5, we're given vector A to be 1/2, -2/3, and 3/4. Which of the vectors below will be parallel to A? So to start this out, we'll treat the vectors A, B, C, and D. They're going to be my vector B in the definition. So what I want to do is I want to take 1/2 and divide it by 6. And 1/2 divided by 6 is 1/12. Now, I'm now going to take -2/3 and divide it by -4. All right, well, if I divide that, that's going to be a positive 2/12. Again, think of the -4 as being over 1. You multiply by its reciprocal, you're going to get a positive 2/12, which is not 1/12. So stop. Don't go any further. They're not parallel. All three ratios for C, when you divide these, have to be the same. All right, for part B, we're going to go 1/2 divided by -1. That's -1/2. -2/3 divided by 4/3. Again, think about multiplying the -2/3 by 3/4. Your 3's cancel. -2/4 is now -1/2. That's a match. Then 3/4 divided by -3/2. Again, multiply by the reciprocal. We're going to get 6 over -12, and that reduces to -1/12. Or you can do some canceling, same concept. But since all three factors are the same, yes, those two vectors are parallel. Part C, notice in this vector there's a 0 as the y component. So if you look at the y component division first, -2/3 divided by 0 is undefined. There's no way they can be parallel. End of story. 1/2 divided by 3/4, 2/3 for part D. -2/3 divided by -1, positive 2/3. Okay, we're getting there. We'll do the last one, 3/4 divided by 9/8. So that is also 2/3. When you multiply 3/4 by 8 over 9 and reduce it, we get 2/3. So yes, that is parallel. Next, we're going to talk about projections. So you might want to be watching this several times. Projection, the rays to the left show the representations of vector PQ and vector PR of our two vectors as A and B with the same initial point P. If S is the foot of the perpendicular from R to the line segment containing PQ. Remember, we were doing those projections of the point onto the X and Y and Z axis back in 11.1. Okay, here comes those projections back, but now we're doing vectors instead of points. What we have is a vector projection of B onto A, and it's denoted as projection of B onto A. So you read the subscript last. Again, think of this as a shadow. So here's vector B. It casts a shadow right onto PQ, which is your vector A, and that red vector, that's going to be your shadow. Red vector, shadow. Even if it goes past vector A, so be it. Even if it goes in the other direction of A, so be it. Those are all my vector projections of B onto A. Now, the scalar projection of B onto A, also called the component of B along A, so they're interchangeable here, is defined to be the signed magnitude of the vector projection, which is the magnitude of B times the cosine of theta, where theta is the angle between A and B. So if we go up to this first diagram, think of this right triangle, PS, that's going to be my vector projection. That's the adjacent side. B is the magnitude, or excuse me, side B is my hypotenuse. Cosine of theta is equal to vector PS over vector B with their magnitudes. And if I solve for the vector PS, I get vector, the magnitude of B times the cosine theta. All right, so how does this work? The first thing we have to do is you have to take the unit vector of A. If you recall when we talked about unit vectors, and I think we said, oh, let's find another vector with a magnitude of 15. You just multiply the 15 to the unit vector. So here, finding the direction is finding the unit vector. And then after that, we find that scalar projection, or the component of B along A, and multiply that to our unit vector. So again, bold notation or with our little arrows. So this is your unit vector. The magnitude of your vector projection, vector PS, is the magnitude of B times the cosine of theta. So the projection is the unit vector times the scalar projection, or your component. All right, so if you recall, because we might not be given the angle between our vectors, we're just given their component form, we need to substitute out cosine theta. We had that corollary that said cosine theta was A dot B for the vectors over the magnitude of A times the magnitude of B. So we're going to substitute that in. And that's going to be our projection. Now, I'm going to clean that up on the next slide. However, there's one more type of projection that we have to look at in this diagram before we move on. And we have to add these in. All right? And those are the orthogonal projections. If you notice, all my dotted lines have those purple vectors going from S to R. That is your orthogonal projection of B onto A. All right? So that's the name of that vector, and we can find that value too. Normally you would think, oh, well, that would be the opposite side. I'll just do sine of theta is equal to the magnitude of SR to the divided by the magnitude of the hypotenuse B. The problem is most times we're not given theta. All right? Okay, so simplifying that statement. Well, as you can see, magnitude of B will cancel with magnitude of B. Now we're left with the unit vector being multiplied by A dot B over the magnitude of A. This part here, that's my projection of B onto A. So when I get those two parts right there to cancel, once I make that substitution, that's the scalar value. All right. There are three forms to write this formula. You can think of it just as it is. A lot of people like that one. You can think about, hey, we got the magnitude squared, so I'm going to move this denominator over to here and square it, which is fine. It's still the same thing. And some people like to use that one property that says, oh, the magnitude of a vector squared is A dot A. Either one of these is acceptable to use. As long as you write it out as part of your work, we're good. I'll know where your thought process is going. All right, so again, there's our definitions. This is the ones you predominantly will see as you go through the work. All right? Okay, now, orthogonal projection of B. Told you can find that projection. It's going to be vector B minus the projection of A onto B. So when you find this vector, you will be subtracting it from B, and you will have the component form of that vector. All right, so that's this part here brought down and subtracted from the B. Okay, now again, if they switch the letters around, okay, let me go back real quick here. If all these letters change, instead of B and A, they have a C and a D, then everywhere you see the B, you make it a C. Wherever you see the A, you make it a D, and everything works out. Okay? Okay, so example. Find the scalar projection and the vector projection of B, which equals 1, 1, 2, onto vector A equals negative 2, 3, 1. So this is all set up, vector B onto A. So we want to look for that shadow. All right, so what do we need? Well, we're going to need the magnitude of A. No matter which one we use, we got to find the magnitude of A. So let's go find that right away. So negative 2 squared, 4, plus 3 squared, 9, plus 1, that's going to be the square root of 14. So find the component vector. All right, we're going to find that scalar value. So A dot B, and then we'll divide it by the square root of 14. So 1 times negative 2, 1 times 3, 2 times 1. We'll add those together. We get negative 2 plus 3 plus 2. All right, those two cancel out, leaving me 3 over the square root of 14. To find my projection of B onto A, we have the A dot B over the square root of A. That's what we just found. And now simply multiply it by the unit vector. So we'll just transfer this to here. And your unit vector of A is the negative 2, 3, 1, all divided by the square root of 14. Well, we're going to multiply these two together. And that's going to give us 14 in the denominator. So we have 3/14 multiplied to negative 2, 3, and 1. And so there's my projection of B onto A. That's the component form of that vector, the red vectors we saw in the diagram. Now, if we're asked to find the orthogonal projection, then we take vector B, 1, 1, 2, and we subtract this answer from it. Well, okay, we're going to need some common denominators here. So 1 minus a negative, okay, that's going to be a plus 3, 7. So 7 over 7 plus 3 over 7 will be 10 over 7. 1 minus 9 over 14. So 14 over 14 minus 9 over 14 is 5 over 14. 2 would be 28 over 14 minus 3 over 14 gives me 25 over 14. That would be the purple vector's component form.